So one last thing to clarify about this whole radical expression thing is the idea behind it, which I think might help you make some sense of some of the questions in number 3 if you haven't yet done some of them. Now, in number 3, letter A, what this expression, the fourth root of x to the power of 5, really means is a little bit more complicated. So I want to make sure that we understand how this works before we take too much time to really belabor the point. A root, by definition, is a number of multiplications. A square root, for example, is 2 multiplications, something times itself. So a fourth root is something that multiplies 4 times. And what this problem is really saying is you have something times something times something times something 4 times that's going to give you x to the 5th as an answer. Now that's a weird thing to think about, and that's why the idea of the fraction is kind of needed, because when you think about it, there's no real easy way of saying, hey, something that, or 4 of something will give you x to the 5th. Like intuitively you're like, wait, what? No, like 5. I need 5 of the thing. But the fourth root is telling you, no, you're only allowed to multiply 4 items. So that's actually why when you write your answer in the box of x to the 5/4, that it works, is because what we're actually saying is if you take x to the 5/4, 1, 2, 3, 4 times, the little root number tells you how many times you're supposed to take it, then that means you'll end up with x to the 5th as your total. And if you remember how exponents work, that actually does kind of make sense. Remember how exponents work? When you're multiplying a bunch of things that have the same base, you can add the powers. 5, 10, 15, 20 over 4. 20 over 4 is 5. So that's why it works. And it's crazy to think about how it works, but generally speaking, the root number, the number on the left attached to the root symbol or attached to the radical symbol, is the number of times that root counts for. So if I was looking at, for example, letter B is a 6th root, which means it counts for 6 multiplications. Something times itself, 1, 2, 3, 4, 5, 6 times, is going to give us an answer of x. It doesn't have any extra powers there, and that's why we would say, well, it's just going to equal to x. Something times itself 6 times is going to give us that x. And we would say, well, what could possibly work? I mean, x is really just 1x. So if you think about it, I must need a bunch of little fractions that add up to 1x at the end. And if I think about it logically, I need 6 of them. Let's think about this way. X to the 1/6. 1, 2, 3, 4, 5, 6 sixths. If I add those fractions, 1, 2, 3, 4, 5, 6 sixths, x to the power of 6, 6, is equal to x to the power of 1, which is x. So that's why the answer in letter B is x to the 1/6. And some of you may have figured that out naturally because you would have said, oh, well, there's an invisible power of 1 here on the right, so 1 over 6 is 1/6, and that makes sense, okay? So the idea is basically to use this number on the left-hand side, this root number I've been calling it, as a counter. That tells you how many times the root counts for. Now, the reason I want to make sure that I say that is because we have experience with roots already. We've been doing problems like this, the square root of 49, since probably late elementary or middle school, and we know what that means. By default, the square root of 49 means something times something that gives us 49 as an answer. But notice how by default a square root counts as a multiplication of 2 numbers. Even though we've never seen it there has always been a little 2 outside attached to every square root. And that code is what tells us something times something that has to be 49. Now, of course, you can think of this as 7 times 7. We know that already. But now we're also seeing that technically this is 49 to the 1/2 and 49 to the 1/2. That also works. And in case you're like, whoa, what? That works? It totally does. Think about it. 49 to the power of 1/2, 2 of them. the second root of 49, or the square root of 49, and another square root of 49. Square root times a square root would square, so you'd have square root of 49 squared, and square squared, you get 49. So there's some interesting little math magic that seems to be happening, but generally speaking, the moral of the story is this. The number outside of the root on the left, the number that I call the root number, is basically a counter. It tells you how many times the multiplication should occur. So start to think of every root, square root or otherwise, as a root in this expression, or a form in this expression. A square root counts for 2 multiplications. A 6th root counts for 6 multiplications. A 4th root counts for 4 multiplications. And just remember that every root counts for a number of multiplications. By default, they will tell you what the root counts for. If they don't, like in letter E, you can assume it's a traditional square root that counts for 2 multiplications. So notice in letter E, I added my own little 2 there. It is completely okay to do that. In fact, we might need to do that, because remember how in letter E they want us to write the fraction? Well, I need a number here on the left to know what my denominator of my fraction is going to be. So now I can tell if I write this as a fraction, I'd have x to the power of, remember the power is the numerator, and the denominator is the root number, 4 over 2. Now, of course, 4 over 2 is totally correct, but if you want to clean that up and just reduce the fraction, you could also call it x squared. And you'll see on the answer key, I probably will consistently reduce my fractions, not that you have to, it's just an option. But that's, again, just something to get used to. This is all new. This is all kind of interesting and weird, but hopefully it's something that you can start to get used to on your own after you've noticed some of these patterns. So finish question number 3, and then in the next question, we'll make sure that we start tying some of these ideas together.